Hello, today we're going to start the notes for the newest unit, Unit 4, Acids and Bases. So we're going to just start off with the introduction of 4.1. So some of this is going to cover the stuff that we've done previously in your science classes, and some of it is going to be a little new. So I don't think you went through much acid and bases last year in Chemistry 11, but you would have done quite a lot about it in Science 10, dealing with the pH scale and then how to identify and name acids and bases. So in all previous classes, you have probably been told that all acids are compounds which formula begins with a hydrogen, and bases are compounds whose formulas end in a hydroxide. Even though this is pretty simplified, it's actually just one of the several definitions of acids and bases that we're going to be talking about. So we're going to first start off with what you've probably already talked about in Science 10, but may not have been told that this is what it was called, but this is the Arrhenius definition. This definition states that an acid is any substance which will produce hydrogen ions in solution. So we have an example of some hydrochloric acid dissociating water to produce hydrogen ions and chloride ions. Remember back to Science 10 when dealing with the pH scale, this is really just a logarithmic scale that is looking at the concentration of our hydrogen ions present. So the more hydrogen ions present, the more acidic something is. According to this definition, a base is now any substance that will produce hydroxide ions when dissolved in solution. For example, sodium hydroxide, we have this hydroxide at the end, so we know it's a base. When this dissociates, it makes sodium ions and some hydroxide ions. Also, according to the Arrhenius definition of acids and bases, they talked about a salt being a product of a neutralization reaction. So a neutralization reaction is simply a double replacement reaction between an acid and a base. And it always produces a salt, so that is our metal and our nonmetal, as well as water. So if we skip down to the bottom here, we see a generalization of a neutralization reaction. So an acid and a base, they'll come together to produce salt and water. So for example, hydrochloric acid is sodium hydroxide. According to our Arrhenius definition, we know that hydrochloric acid starts with an H, would produce hydroxide ions in solution, is an acid. Our sodium hydroxide ends with hydroxide, would produce hydroxide ions in solution, so is a base. They come together to produce our salts, sodium chloride, and some water, H2O. Now, just some general properties of these types of acids and bases. So our acid can be neutralized by a base. It has a sour taste. So for example, a common acid is lemon juice, so it's very sour. It will turn litmus paper red. So our litmus paper is just one form of indicator that we can use to test for either an acid or a base. Remember also, acids have a pH that is less than 7, whereas our bases have a pH that is greater than 7. And if it is around 7, then it's going to be neutral. So if anything has a pH under 7, it would turn our litmus paper red. Often acids also, these Arrhenius acids, react with metals to produce hydrogen gas. So for example, in one of the labs that we did, we had some magnesium, we added some hydrochloric acid, and in turn we got magnesium chloride and hydrogen gas released. On the other hand, our properties of these Arrhenius bases, so bases that end in our hydroxide, can be neutralized by an acid, so go through this neutralization reaction. They have a bitter taste, so for example, baking powder is a base, has a very bitter taste. It will turn litmus paper blue, so anything with a pH greater than 7 will turn blue in the presence of our litmus paper. And it feels slippery to touch, so another common base would be soap. Soaps are made up of different bases. They feel very slippery. If you're wanting a little way to remember the litmus paper, which turns red and which turns blue, remember red and acid both end in D, whereas blue and base both start with B. So acids will turn red in litmus paper, bases will turn blue. So that's all well and good. However, we find this definition of acids is a little too restrictive. For example, there's many other compounds that don't follow these rules that are acids and bases. So another definition was made, and this is the definition that we're going to be using for the entirety of the rest of this acid-base unit. And that is our Bronsted-Lowry definition. So this definition goes that an acid is any substance which donates a proton. So we call acids proton donators. Now, our protons are always going to be denoted by this hydrogen ion. Remember, a regular hydrogen atom has one proton, atomic number 1, and will have 1 electron. Now, our hydrogen is the only atom that does not have a nucleus. It is only made up of the 1 proton, or sorry, does not have a neutron. Still has a nucleus. Does not have a neutron. It is made up of 1 proton in the nucleus and 1 electron. Now, when our hydrogen turns into an ion, we still have the 1 proton because it can't be hydrogen without 1 proton, but now we've lost the electron. So we now have a positive charge. So basically, a hydrogen ion is really only just our proton. So acids are a substance which will donate a proton or donate a hydrogen ion. A base is a substance which will accept a proton or accept this hydrogen ion. So we call bases proton acceptors. Now, according to this theory, acids and bases must coexist. So they always have to come in pairs, and this should make sense. We can't donate a proton unless there's a willing acceptor. A base cannot accept a proton unless it has been donated by another substance, so an acid. So let's consider dissolving some hydrochloric acid in water. Let's work through that example. So we have some hydrochloric acid plus our water here. And when that happens, our hydrochloric acid is acting as an acid, hence the name. So it's going to actually donate a proton. Now our water here is going to have to accept the proton, making our water a base. When our water accepts a proton, it now becomes, instead of H2O, H3O. It has been a neutral, water was neutral, it has gained a positive, so it now has an overall positive charge. This H3O is called a hydronium ion, and this is what we're going to be using throughout the whole unit as well. We're not just going to say that it turns into just a proton, because a proton won't actually exist by itself in solution. It's super small, it's positively charged, it's easily going to be drawn in by that partial negative part of a polar molecule water. So instead of just dissociating into a proton and chloride, the water picks that up, we get a hydronium ion and our chloride ion. So the fact that water here was accepting a hydrogen, accepting our proton, this makes hydrogen a base. So see how we have an acid and a base both at the same time. Now let's look at another scenario here. Let's look at ammonia. Ammonia is considered a base because it accepts a proton from water. So our water here has lost our hydrogen ion, it's lost our proton, and it's gone towards our ammonia. So our ammonia here is our base. Because our water has donated this proton, it is now an acid. So in this reaction, our ammonia turns into an ammonium ion, now gaining a positive charge. And our water, which was neutral, has now lost our proton, so lost a positive charge, now becomes hydroxide and has a negative. Now I can always tell that I've done my charges correctly if my charges on either side are balanced. So here I have an overall charge from ammonia and water, an overall charge of 0. On my right side, my ammonium ion is giving me a positive charge and hydroxide a negative. So once again, an overall charge of 0. So I can tell I've done the charges correct by making sure they are balanced. All right, two more things to talk about here. There's something called amphiprotic substances. So an amphiprotic substance, for example, water, can act as either an acid or a base depending on the situation. So that's what we call amphiprotic. They can either be an acid or a base. So one common amphiprotic substance is our bicarbonate ion. So I've drawn here what happens when we take the exact same ion, react it with water, but in one instance it's an acid and in one instance it's a base. So when it's acting as an acid, remember an acid is a proton donator. So if it's acting as an acid, it is going to donate this hydrogen to my water. My water is accepting the proton, so therefore it's a base. On the product side, I will have lost this hydrogen, therefore losing a positive charge. I already had a negative, so this now becomes just a carbonate ion with a -2 charge. When my water has gained a proton, it now becomes this hydronium ion. Now I'll double check. Sorry, screen went blank there. So I'll double check that I've done the charges right by checking to see if my charges are balanced. So on my reactant side, I have a -1 charge and 0 from water, so an overall -1. On my product side, I have -2 from this carbonate ion and a +1 from my hydronium, so an overall of -1 as well. Now let's look at my bicarbonate acting as a base. So if it's acting as a base, it is going to be accepting this proton. That means my water must be acting as an acid and donating the proton. So I'm losing this hydrogen from my water to my bicarbonate. So therefore, my bicarbonate here has gained a hydrogen, gained a positive charge, so now is neutral. And my hydroxide has lost a positive charge, my water has lost a positive charge to become a negatively charged hydroxide. And once again, notice how I have a -1 charge on both sides. So we're going to be coming across a couple examples where certain substances can act as either an acid and base, and that is okay. That just means it's an amphiprotic substance. The last thing I'm going to talk about today is conjugate acid-base pairs. So as previously mentioned, acids and bases, according to the Bronsted-Lowry theory, must exist in pairs in order for one thing to donate a proton and the other accept it. So let's once again look at my system of ammonium. So I have ammonia acting as a base, so therefore it's accepting a hydrogen. Therefore, my water, which is donating it, must be an acid. But let's look at the reverse reaction because this is an equilibrium. So this reaction could happen in both directions. Now going in the reverse direction, my ammonium ion is now the one that is donating, so it is an acid. And my hydroxide now would be the one accepting to go from OH to H2O, so therefore it's a base. We call these on either side of the equation conjugate acid-base pairs. So I have my ammonia here as a base, so its conjugate acid would be ammonium. I have water here as an acid, so its conjugate base would be hydroxide. Base, conjugate acid, acid, conjugate base. So a conjugate acid-base pair is a pair of species that only differ by one proton. Sorry, this should say one. Only differ by one proton. So just be careful when you're finding out which one the conjugate acid or conjugate base is. You might have to work a little backwards. So remember, our acid is one that donates. So if we have a base and we're looking for the conjugate acid, we're looking for an acid that is going to be able to donate a proton. So when working backwards, notice when I'm looking at an acid and trying to find the conjugate base, I have lost a proton. Because working backwards, this base will now be looking to accept one. When I'm starting with my base, for example, ammonia, and moving to look at the conjugate acid, notice how I have gained a proton. Because if this is now my acid looking to turn into a base, I would be losing a proton. So just watch our terminology here. So an acid is one that will donate a proton, and a base is one that will gain a proton. However, the conjugate base of an acid has now lost a proton from the acid, and our conjugate acid has now gained a proton from the starting base. So I'm going to work through two problems from a couple sections here. So in the first one here, you were told in your notes that this is an acid and this, for example, is a base. So what would my following conjugate acids and bases be for each equation? Well, if this is an acid, this is the one that is donating the proton. So I have lost a positive. This will become negative. So I have Cn minus, my cyanide ion. Because my water was a base, it is accepting the hydrogen. So this is turned into a hydronium with now a positive charge. Let us do one more. I believe you were told that this was the acid and water again was the base. So just remember which way the protons are being donated. My acid is giving a proton to a base, my base is accepting it. So I've lost this. This now will become a phosphate ion with a -3 charge. It was at -2. I've lost a positive, so it's now -3. And my water has now become a hydronium once again. It has gained an extra proton, so gained a positive charge. Let's work through two of these. Let's work through maybe D and A. So I'm looking for either the conjugate acid or base of the following substance. So if I'm looking for the conjugate acid of this HPO4 -2, that means this right now is the base. So my base is going to want to gain a proton. So to find the conjugate acid, I'm going to add a hydrogen. So I've added a hydrogen there, I've added an extra hydrogen, and therefore my -2 charge becomes just a negative. I've added a positive charge. And this should be able to work out because when I'm looking at these two substances, I notice that this one has gained, so this must be my base. This one going in the reverse direction has lost, so this must be my acid. So yes, this is the conjugate acid of my initial base. Let's look at D. I'm looking for the conjugate base of hydroxide. So that means my hydroxide must actually be my acid. And my acid is going to be losing a proton. So this is my acid losing a proton to get my base must mean I'm losing the only proton I have, losing a positive charge, so I get just an oxygen ion. This makes sense because if this was my base, I would be gaining my proton. So the conjugate base of hydroxide is an oxygen ion. So this is just a way that you will be able to work backwards to find the conjugate pairs. I hope this has been helpful. If you have any questions, this is what I'll be discussing next study session on Wednesday. So please tune in for that, and that's all for now.